Welcome to the Explainer. Today, we're zoning in on a fundamental property of radio waves that, honestly, can either make or completely break your system design. Now, just for some context, this is part 10 of a pretty extensive 20-part series. It's all based on a really detailed report on RF propagation from the team at RFI Detectives who are part of Virtualization Options LLC. Today, we're going to focus on one of the most basic choices you have to make in system design: polarization. And specifically, we're talking all things horizontal. All right, so let's start with the absolute foundation. What are we really talking about when we say a radio wave is horizontally polarized?
Okay, so here's the key. It's all about the orientation of the electric field. Just imagine that wave traveling straight ahead. For horizontal polarization, its electric field is oscillating from side to side, parallel to the ground. It seems simple, but that little geometric difference has some massive implications for how the signal performs.
So, now that we know what it is, let's look at where you, as an RF professional, are actually going to run into this. This isn't just some textbook concept, it's a very deliberate design choice that engineers make every day. All these applications, you'll notice they share a common thread, right? They're typically fixed links. Situations where having control over the signal path is absolutely critical. We're talking about a broadcast tower to your house, a microwave dish aimed at another dish, or a directional HF beam. The goal is always a stable, predictable connection. So, why do engineers pick horizontal polarization for these jobs specifically? Let's get into the nitty-gritty advantages that make it the right call, even if it sometimes means a little extra work with alignment.
Well, the benefits really center on two things: improving signal integrity and predictability. And these are, as you know, critical for a robust link. When you choose horizontal, you're basically creating your own private lane on the RF highway, keeping you isolated from all that busy traffic from vertically polarized mobile signals.
And this quote from the source material it nails it. This is the main reason you'd use it in today's crowded spectrum. It's all about creating that clean, interference-free channel for your fixed link when you're surrounded by a sea of other signals. Now, this is a really big deal for any of you who've had to calculate a link budget. The way horizontally polarized waves interact with surfaces, especially the ground, is it's more predictable. That consistency, particularly when you think about phase shifts during reflection, lets you model things much more reliably and get a way more accurate picture of how that signal is going to behave. But of course, no single solution is a silver bullet for every single problem. So let's be real and look at the trade-offs, because understanding when not to use it is just as important as knowing when to use it. This chart really lays out the fundamental trade-off perfectly. Horizontal is your go-to for controlled, fixed links where you can dial in that alignment for the best possible interference rejection. Vertical, on the other hand, that's the king of mobile applications, where an antenna is always moving and you just need something that works without perfect aiming. So the bottom line is that any so-called disadvantage is really just about context. It's all about what the application needs. The very thing that's a pain for a mobile user, needing that precise alignment, is actually a key feature for a fixed point-to-point link. Okay, let's wrap this all up into a practical framework you can actually apply to your next job. How do you decide when it's time to pull the trigger on a horizontal polarization design? Just use this simple checklist. First off, is the link fixed? Second, do you desperately need to keep it isolated from all the noise of mobile signals? And third, is a predictable path absolutely critical for your link budget? If you're nodding your head yes to these, then horizontal polarization is almost certainly your best bet. And please remember why this all matters. We're not talking about tiny little gains here. The source material points out that a simple polarization mismatch, trying to catch a horizontal signal with a vertical antenna, can cost you up to 40 dB of signal. That is a massive loss that no amount of power is going to fix for you. So as we finish up, I want you to think about your own systems. Is there a nagging interference problem you're dealing with? Or maybe a link that's just frustratingly unstable? Could it be that the elegant solution you've been searching for is as simple as rethinking its polarization? It's a fundamental choice that's always worth another look.